Hello and good afternoon to everyone. My name is Amarnath Bhatt from Softcast Technologies, Bangalore. My co-author is Stephen Barnett from INCAST Consultancy in England. This presentation is about how casting simulation could possibly help address the foundry industry's challenges due to the COVID-19 situation today. Static or reducing demand. Modern Casting issue of August reported that over 70% of the foundries face a decrease in business. Similarly, Stephen Pilbury in June issue of INCAST said overall the global market for PIC is recessive. Some of these problems, supply chain disruptions, labor migration, cash crunch, bankers not very keen to lend, and poor fund flows. All in all, a very difficult economic situation. Now, how can the foundry industry cope? As Mr. Sanjay Shroff, president of the IIF, said in a recent issue of the Foundry Journal here, introspection is the only option. The external factors are becoming more and more stringent. So we need to look at what is within our control, look within, and that probably is the best option for the foundry, save by eliminating wastage. The foundry industry worldwide is cost intensive. Out here, it's also labor intensive. What are these costs? Some of the obvious costs are energy, material, labor, and so forth. But some of the not so obvious and often quite latent or hidden, the costs are wastages. And these lead to substantial opportunity losses. What can the foundry do? What are these factors that are within the foundryman's control? A, minimization of specific consumption of energy, material, and so forth. Eliminate, maybe to start with reduce, but eliminate shop trials and disruptions. Prevent as cast defectives and ensure a sustained state of not only first time right, but every time right. All this will lead to quality outcomes that directly lead to benefits such as cost savings. Now, the key thing in all this is prevention of wastage. Whether we do more trials, whether we have as cast defectives, our yield is poor, it all boils down to wastage. So if we prevent wastage, it translates to opportunity gains. As Philip Crosby wrote in his book called Quality is Free in 1980, quality improvement is through defect prevention. And as all of us know, prevention is always better than cure. Now, where does casting simulation come into all this? Now, if you look at the goals on the shop floor, quality improvement, yield improvement, as more critically, defect prevention and elimination of trials, all these are not very well served by just manual means alone. Manual methods, they do not hold a promise of significant mitigation of the problem or the situation over the long term. What is needed is computer-aided solutions. Now, how is this possible? By eliminating defects, by enabling correct understanding of the casting's behavior, by delivering accurate methoding, and by virtual confirmation of the given design, all of this before we actually produce on the shop floor. This would result in physical trials being eliminated, yield being optimized, defects being prevented, and quality being delivered. Of the various functional areas in a foundry, broadly we can classify into three: design, production, and then finishing operations. The most critical, the most vital one is methoding. So this is directly linked to product quality, yield, shop trials. Most importantly, it is the single biggest factor that is almost completely within the foundryman's control. Now, for a method to be effective, now what we mean by this, it should consistently deliver defect-free castings. That means it should be robust enough and accurate enough to consistently deliver defect-free castings. It should be accurate in all design aspects, with regard to all the principles and so forth, but it should factor in the foundry's constraints and capabilities. Now, all this means that you need a computer-aided approach because manual means by themselves are prone to error. So we therefore focus on design and improvement of methods using computer-aided tools such as simulation systems. What can they do? They can prevent defects, assure quality, improve yield, eliminate trials, shop trials, which are a complete waste, and make the method robust. Now, all these outcomes contribute to reduction in overall operating costs, and this is a very important goal to achieve in the current difficult times that we are going through. Now, what is the approach that we have used in this study? A few case studies have been taken up and we are presenting them to illustrate the positive impact on cost savings resulting from defect prevention, quality and yield improvement, and elimination of shop trials, all with the help of a casting simulation and methoding system. The investment casting project studied were 3 each at 3 foundries in India, all in Rajkot, and 1 project at a Hungarian foundry. This study determines approximately, we have to depend on the foundry's inputs, and to some extent they are approximate. So approximate savings that they have achieved on various factors resulting from these improvements by using simulation systems. So 3 important improvement areas: elimination, initially reduction of shop trials, quality improvement, and then yield improvement, all the time delivering the required quality. Those are our key result areas and goals. Now, the IC investment casting units used in this study, as you can see, there are 4 units. Unit A is the Hungarian foundry Magyarmet. Unit B, C, D are 3 investment casting units in Rajkot in India. The Hungarian foundry, the alloy for this casting end section, this was haste alloy. And the foundries in Rajkot, mostly you can see they're all WCB castings that were used for this study, barring a few which were stainless steel castings. The Hungarian foundry was by far the largest, the biggest, and the most spread out, whereas the others are small to, let's say, medium-sized castings. Now let's look at each of these case studies in a bit of detail. The first one is this haste alloy component from Magyarmet, N casting, the name, 40 kgs haste alloy casting. And you can see that's those are the pictures of that component. The stage 1 was the foundry's customer. They didn't have a CAD model, or they didn't have drawings and so forth, but they gave a sample component. A 3D model was, solid model was generated by physical measurements. And then a step file was generated once the model was obtained. And this was used for casting simulation to identify its castability, to determine its castability rather, to identify major hotspots, understand the freezing patterns, where we might get defects and so forth. And once this was understood, a few methoding ideas were developed, the trees were developed, and those were then simulated to establish a quality standard. And then finally, once the final method or the final tree was selected based on the study of all the designs, it was implemented on the shop floor and found to be 100% defect free. So that's the casting there, and some of the simulation outputs you can see, temperature maps and hotspots and so forth. Some of them are shown in this presentation. So the simulation results essentially focused on temperature maps. This profile the distribution of temperature across various sections, hotspots at different intensity levels, and what we call as heat intensity traces. These results, they showed the required locations of the gates, where one needs to apply the gates, what kind of freezing patterns and feed flow paths are set up. From the initial information, a number of different designs were generated, right from very sort of high yield designs to lesser yield designs, but more robust and more, and shall we say, safer. These were thrown up, and finally, after studying these few designs which were simulated, a design with 4 gates on either side was chosen. This was simulated, but then we found that there were some problems at 2 ends, and further some more gates were added. And that was the final design that was implemented on the shop floor. As you can see, the component out there in near the slurry tank. And these were implemented on this final design was implemented on the shop floor. Now let's look at some of the monetary benefits that were gained in this foundry through this casting simulation process. It was prior to this, the foundry used to do manual methoding, and every job they would estimate certain number of additional components to be cast in order to take care of probably defectives and damages and so forth, like a buffer. But with in this particular instance, they estimated that 13 additional castings would be required. The order quantity was 17, so they thought of making 30 castings uh, in order to take care of possible defects and so forth. But with the casting simulation, they decided to produce only 6 extra castings, thus saving 7 castings. These 6 additional castings were produced mainly to account for possible losses during damage, from damage during handling. This translated to a saving of over 15,000 euros. And with that kind of saving from just one component, they decided to go in for a simulation system. They said this is worth it. Now that was one project at Magyarmet. We have a few projects at each of the 3 Rajkot foundries, one in new product development, just like the Magyarmet case, one quality improvement, and one yield improvement. So this is the first project, first casting at one of the foundries. We call it, let's say, Unit B. And this is a new product development job. It's a valve body. As you can see, it's about 15 kilos steel WCB casting. Those are the pictures, not very big. Some of the simulation pictures you can see here, the outputs, temperature maps, and feed flow paths and hotspots and a few other things like that. The results again, the main results like temperature profiles, the hotspots and intensity traces. Again, showed the required location of the gates, where one needs to apply the gates, the freezing patterns, and so forth. Based on that, a method design was developed after looking at the casting simulation results, and the gates, the feeder bars, and so forth were computed, 3D model generated. This was simulated, and it showed that there would be no defects. This was then poured and actually checked on the shop floor. RT level 1 achieved as against a requirement of level 2 with a reasonably good yield. So the gains from this particular casting simulation job, there were no physical trials. They simulated on the system, they saw the results, developed the design, simulated the tree, and cross-checked that it would be okay. They poured and they found it was okay. So good quality, good yield, and no physical trials. The same foundry, another job was taken up where essentially it was a quality improvement job, but as it so happens, they also got a little bit of yield improvement in this case. And this was a stainless steel component. As you can see, they call it the stuffing box. Again, similar process where first the simulation of the casting is done and try to understand the castability, the casting behavior, and determine where one should apply the gates and so forth. And later on calculate the gates and the feeder bars and so forth, and develop the tree. So same thing, understand castability. In this case, they try to figure out which is the best orientation and then where's the location of the gates. Here again, they had a project for this particular job before running it through the casting simulation process, where they had done a manual method on the shop floor, and this was simulated. So this was a existing method which was there before, and they found on the shop floor they found L3 level defects, which also showed up in the simulation. This method was not okay. Then a new system was designed, and this system was implemented after checking on the simulation system. It was found to be okay, and this was implemented. They found that this method is okay. There was a minor gas porosity, but it was acceptable, and the rest of it was NSD, and they got a slightly higher yield also in the bargain. The same foundry, a third job was done, which was essentially aimed at yield improvement. And this again was a stainless steel component called a drive shaft. And that's what it looks like. Again, similar process was used. Casting was first simulated to understand its castability and determine the location of the gates. In this case, what the foundry did was they came up with three possible designs, and they decided to model all of them and simulate all of them and try to figure out if all of them, if whichever gives a good quality, which is likely to give us the best yield. So the idea was to try different things on the computer and select the one which had the best yield. This was the first method that was tried, and this was also poured and checked on the shop floor. Sorry, it was found to be okay. RT level 2 achieved about 40% yield. Another quite similar method was developed, a tree, slightly different gates and orientation of the gating also. And this was simulated, found okay, also checked on shop floor, but very similar yields and not much of difference from the first one. Then they came up with the third one, and this was also checked on the system, found to be okay, poured on the shop floor, and here they got a little bit of higher yield, and then they decided to go in with this particular method. So this is a case where they tried different ideas after simulating the casting, and checked all three to see that they are all okay, and then selected the best. Now, if you look at a summary of this particular unit, the castings that were done, one was the NPD, new product development, the other was quality improvement, and the third was yield improvement. And you can see that there were considerable savings. I mean, we are looking at the savings of each, I mean, just one of those components in each case. The significant financial gains secured are as follows. In the first case, no shop trials. So they got a savings of about $126. This was a order quantity of 200 numbers a month. So this saving is essentially the fact that they didn't have to do a shop trial. So the savings due to no trial on the shop floor. The other one, quality improvement from a 100% reject to a 100% okay NSD level. So this again was a regular repeat order, roughly 250 numbers a month. So this resulted in a savings of 1,800 odd dollars per year. The last one was where they selected the best method from a yield perspective across the three designs that they came up with. And the savings in this case, because they implemented the best one compared to, let's say, the others, was about 800 odd dollars per month, per year. So overall, I mean, just looking at these particular items, so you can see that there are considerable savings. And if you sort of extrapolate over the other castings that they produce, the savings are considerable. The next unit, we will call it Unit C. Again, similar approach, one new product development job, one quality improvement, and one yield improvement. This particular one is a CF8M bonnet component. As you can see, that's how it looks. Again, a very similar procedure which is adopted is first simulate the casting. This helps us understand its castability, its defect potential, and therefore, how does one go about doing the design, the tree design. So here again, a method was developed based on the simulation results. Feeds or other gates and feeder bars, etc. We computed, a 3D model developed. This was simulated and checked on the system whether we're going to get problems or not, and they found defects, no real defect potential. This was implemented on the shop floor, and they found RT level 1 achieved with a yield of roughly about 34% defect free. The other job that they took up was a quality improvement job. This is a very small component, about just 1.5 kilos, and WCB. You can see that's the component, a small body component. Again, same process, first casting simulation, and then we go on to the method that was done. This was the initial method that was developed, and this was simulated, found to have some problems. This was implemented on the shop floor. It showed that it was overall okay, but there were minor isolations in the simulation system. On the shop floor, overall, they achieved the required quality, but at certain locations, NSD was required and that was not achieved. So this had to be rejected. They then came up with a new design, which was quite similar to the previous one, but rectified the particular locations where they had these issues. And then this was poured and they found that the quality was okay. The third case in this particular foundry was a yield improvement job. It's roughly about 10 kilo component, WCB. Again, a body type of component. Similar process where different outputs are generated from a casting simulation process. And based on that, we understand the behavior, castability, and the most important, most critical is the location of the gates. Based on this, there was an initial method simulation done, and they found that this was okay, as you can see there. Then they developed another method, and this also was simulated, again found to be okay. But in this case, they found that they had a higher yield, an increase of almost 8% over the previous one. So both were developed, checked on the system, both implemented to check that actually one gets okay quality, required quality. But in the second case, they got a higher yield, and that's implemented. Now, this is a summary of the 3 jobs at this particular unit C, where we have, as you can see, in the first case, new product development, there was no shop trial. So the savings were a small amount of about 70 odd dollars because they did not do any trial on the shop floor and got it first time right. In the other case, quality improvement, they got an improvement of about 100 and odd dollars because again here there were no more shop trials. Once the quality was set, they continued the production. So reduction or elimination of the trial resulted in a saving of about 100 odd dollars. In the third case, this was a yield improvement. So they got an annual savings of about 1,800 odd dollars in this case. This is the last foundry where some of these case studies were done. And as before, the first project was a new product development, an 8 kilo carbon steel component, a body again, roughly, that's the kind of body. This again, similar process of simulating the casting and understanding its behavior and identifying the location of the gates. Again, here, the tree was designed, the gates and the feeder bars and the poke up and runner bars, etc., were all computed from the system, and they developed the tree. This was then simulated to check whether it's going to be okay or not, and then it was poured on the shop floor. Again, higher quality level achieved as against the requirement with a yield of about 37%. In the second study done at this foundry, this is a quality improvement project, roughly about 14 kilo casting, carbon steel casting, again a body, as you can see. This was simulated, the same process is used. First simulate the casting, understand its behavior, and based on the results, design the tree. Most significantly, the location of the gates, and then the computation of the feeder bars and the runner bars and so forth. And in this particular case, again, there was a method which was already existing prior, and this was simulated. They found a lot of problems, and the system also showed significant intensity hotspots in the casting when the tree was simulated, significant isolations. And on the shop floor, they found L4, L5 level defects. A new system was generated, new tree was generated. In this case, as you can notice, the orientation itself was changed. Earlier, the orientation was kind of horizontal, now it's vertical. The feeders were also changed. A feeder which was required at a location was added, and this was simulated, and the result was okay. They achieved level 1. This was poured on the shop floor, and they found that the results were fine with a slightly higher yield than before. The last case in this particular foundry was a yield improvement project. Again, a very small one, 3.5 kilos carbon steel component, a disc type of job. and very similar process. Some of the outputs from the system are seen here, different outputs. Casting simulated to understand castability, etc. And in this case, they came up with two designs. The previous foundry, they came up with three designs. As here, they came up with two designs of tree, and they simulated both to check whether it's both are okay, and then they chose the higher yield tree. So this is the first one, which gave okay results, RT level 1 secured, and a certain level of yield. They then came up with another design, again checked on the system, found to be okay, and this had a slightly better yield. This was poured on the shop floor and then implemented. Now, this is a summary of the financials, I mean, the gains that they got from these in these three projects. The first one, again, the saving of about 90 odd dollars is essentially because there was no need to do a shop floor trial. Directly from the system they saw okay and implemented and checked okay. The second one, a quality shrinkage, a quality improvement job. There was gross shrinkage, as you can see, level 4, level 5 defects. Subsequently, an improved job done on the system, and they got an okay casting with a slightly higher yield. The annual savings because of this was about $500. In the third case, a yield improvement project, between the two, they had a slightly higher yield in the second case, and that gave a reasonably good savings over the year, annual savings over the year. Now, apart from these specific cases, three cases at each of these foundries, and the very first one at Magyarmet in Hungary, apart from these, which are specific to those castings, we interviewed and got a kind of general overall assessment from the owners or managing directors of these three foundry. We did not do this at the Hungarian foundry, but this was done at the Rajkot foundries, where we asked them to assess their general experience of before and after implementing a simulation system. What was the situation before, and what kind of improvements they saw after. Now, here are the results summarized, approximate results. The key result areas are three. One is new product development, two stands for quality improvement, and three stands for yield improvement. So as you can see, before and after, in the case of new product development, there's a sizable improvement in unit B and unit C from before to after, about 75% plus improvement, whereas in unit D, the improvement was about 55, 57. Probably they already had a good record before, so the improvement did not, yield that much, only about 57% improvement. In the case of quality improvement projects, in unit B, as you can see, about 67% improvement from before to after. In unit C, it was about, and D, it was about 50%. That means where it was 2% before, it then became 1%, and where it was 7 became about 3.5% subsequent. This is quality improvement. Basically, what we are looking at here is percentage as cast defectives, reduction in percentage as cast defectives, and that's the quality improvement that we are looking at. Okay, we are not splitting into repairable and reject and so forth, but as cast, what is the level of defectives achieved? And before implementing simulation, some of their experiences which are documented, and after implementing, what is the experience? Now, this is an overall kind of assessment. In the third case, called yield improvement, as you can see, here also there's about 5% increase in each of these cases, from 35 to 40, from 42 to 46 and about 32.5 to 37.5 yield. These are the end results. Okay. Now, the monthly, all this translates to monthly savings based on the averaged estimates of all these three improvement types across all production over the years. So what we did was took these improvements before and after, looked at their production and their uh, previous situation and subsequent situation, and extrapolated from these assessments to the overall savings that that accrued at these foundries. And you can see in the case of unit B and C, the monthly savings, mind you, these are monthly savings in dollars, 8,000 plus, and in unit D is 14,000 plus. Now, if you these savings are overall, use across all these three types. We also did an analysis of the savings because of the individual types, that is individual outcomes by way of reduction in shop trials, by way of reduction in as-cast defectives, and by way of improved yield. And here also, as you can see, in each case, there is a substantial improvement because of improved, substantial gain because of improved yield in unit B and D. And in the case of unit C, it was because of trials, shop trials coming down. Now, this means that prior to implementing simulation systems and doing computer-aided methoding, in the case of unit B and D, the yields were on the lower side, and they jumped up quite a bit through casting simulations solutions. Whereas in unit C, the yields were probably higher, but their number of trials, the shop trials, were much more before. And with the help of casting simulation systems, they were able to reduce the number of trials, and so the higher benefit is shown in that particular instance. So this anyway, if one looks at all these the overall savings, it shows that there is considerable potential for savings, and you know by eliminating wastages in the shop floor, just by using casting simulation and methoding system. So we are more accurate. We need to do less trials. We have less as-cast defectives. We can improve yields, especially important for regular production jobs and not for one-off jobs. So all this together means significant savings. So based on this, we have concluded that one of the things that foundries can do today is to use extensively and rigorously and consistently use casting simulation and methoding systems to do all these, to implement in all these areas and derive the benefits. So systematic yield improvement, systematic quality improvement, and systematically ensuring that trials are eliminated, shop trials, which are a complete waste. So we conclude that casting simulation systems are very, very useful to foundries today. I mean, they were always useful, but today more so because of the extremely depressed economic situation, which means that they really need to conserve, you need to tighten the belts, and you need to conserve money. Finally, I would like to acknowledge the participating foundries, Magyarmet in Hungary, Rainbow Technocast in Rajkot, Delta Technocast in Rajkot, and Micromelt also in Rajkot. These are the participating foundries, and thanks to them, we are able to get some good actual real life data. Otherwise, it's all, mostly it is theoretical. Now, this is where from the shop floor, we have been able to get some real data and use that data for analysis. Other contributors are my colleagues from Rajkot and Bangalore, who contributed considerably to this paper and presentation. Uh, Thank you, everyone. And that's it from me. If you have any questions, you could send them across to ICI Nora, and I would be happy. Both of us, Stephen and I, would be happy to answer to the best of our abilities. Thank you and bye.